just to give you a heads up, a third homework assignment next week, after this one is due. And I just want to give you a heads up that that will be the first serious programming assignment. It'll involve, give you a chance to implement a simple Bayesian classifier, naive Bayes classifier. And we're going to try to auto-grade this with some software, and therefore we'll be asking you to program in a programming language called Octave. If any of you are familiar with MATLAB, it's nearly indistinguishable from MATLAB, except that you don't have to pay for a license for Octave because it's open source. But we'll be providing some material to teach you that. It's a simple interpreted programming language. So those were the announcements I wanted to get out. Before we jump into real content, are there any other questions about just course logistics, organization, or any other comments that I forgot to mention from the TAs or instructors? Yeah?
Will the recitation still be in the same room it has been in? Because there was a million people in that little room. And,
uh-oh.
Yeah. I don't know, maybe a lot of people have dropped since then.
Yeah, let's see. It doesn't look like that many people dropped since then. We'll see if we can get a bigger room. It would be great to have it maybe even in this room. But for now, unless you hear otherwise, that's the room that was allocated to us, and we'll see if we can do better. Note to myself to come back to that. Okay, so today we're going to really begin seriously looking at probabilistic approaches to machine learning. On purpose, we started by talking about decision trees because decision tree learning algorithm is a fairly easy one to get your head around. And it displays a lot of the very general properties that we want to talk about when we discuss function approximation. For example, overfitting and this trade-off between how complex the tree, the fact that there are many different trees that could explain the data, that we have to choose one, that we need some basis for doing that. And so decision tree certainly is widely used in practical applications and worthwhile knowing about. But it's an example of a really non-probabilistic approach to learning. And much of the field in the last 15 years has refocused on more probabilistic approaches. We'll be covering a lot of these in class. Probably some of you have heard about terms like Bayesian belief networks or Bayes nets, Bayesian classifiers. And so today is really our beginning of that. And I'm going to do, we're going to cover a material that for some of you may be old hat, if you're an expert in statistics and probability. But I think it will, for many people, be a more, what's the word, palatable way of getting into the terminology and the concepts that we're going to be using here. Okay, so when we left off last time, we were just looking at the Reverend Bayes and his famous Bayes rule. And this is really key to much of what we do. So let's take a look at that. Remember, we derived that up in the corner there by just pointing out that we could use the chain rule to factor the joint probability of A and B in two different ways, and that led immediately to deriving this expression. Here are two other forms of it that we'll sometimes use. This first form, this one here, is really just like the one up in the corner, except that we've replaced the denominator, P of B, by an expression that's equal to that. Remember, one of the rules of probability is that if we have two random variables, A and B, and we want to know the probability of B, we can simply sum over the two possible values of A, the probability of B given A times that probability, plus the probability of B given not that times the probability that it's not true. And so it's just a simple rewrite. We'll actually more often use this form than we will the one up there. And this bottom one here is just a simple way of pointing out that actually in general, we can put anything else here on the right, on the condition side, in addition to B. So we can put anything else here. And the more, this is in some sense a more general form of Bayes' rule. And again, it's not hard to prove this one from the basic rules of probability. Okay, so let's just to make sure we're all on the same page here. Let's take a quick look at a concrete example. I worked out the arithmetic in advance, so I'm pulling out my notes. But let's suppose somebody just coughed. Somebody did just cough, I heard it. I wonder if they have the flu. If you're sitting next to that person, you might be wondering if they have the flu. Nothing personal. But if you were a Bayesian, you might think about that question in the following way. Suppose, let's define two random variables. A is that whether you just coughed or not. Sorry, A is whether you have the flu or not. B is whether you coughed or not. And we might, furthermore, if we're going to use Bayes' rule, we have to now define some probabilities that Bayes' rule requires. But if we want, we could use Bayes' rule to ask the question, well, what's the probability that you have the flu given that you did cough? And if we define A to be flu and B cough, then we can use Bayes' rule as shown up here. And of course, we're going to have to define some probabilities. So I might say, well, if A is that you have the flu, what's the prior probability that somebody has the flu? Maybe in general, pretty low. Today it's the middle of flu season, so maybe 5% probability that you have the flu. What's the probability that you will cough if you do have the flu? Well, just about everybody coughs if they have the flu. What's the probability that you cough if you don't have the flu? Well, many people cough who don't have the flu. Maybe the probability is 0.2. Okay, so if I look at that, then I can use this simple version of Bayes' rule to answer the question. The probability of, I guess now we're looking for the probability of flu given cough. That's going to be just the probability of B given A, which is 0.8. That's the probability that you'd cough if you did have the flu, times the probability, the prior probability that you have the flu, 0.5, over what? Well, this first term is actually the same as the numerator, 0.8, 0.05. And that second term is really just the probability of coughing given that you don't have the flu times the prior that you don't have the flu. So what's the probability of B given not A? Well, we had that here. So it's plus 0.2 times the probability that you don't have the flu. What's P of not A? 0.95, right? Why? Because P of A equals 1 minus P of not A. Okay, so if we plug these in, I did the arithmetic in advance. That tells you the probability that you have the flu given that you just coughed is 0.17 if you believe in these other priors. Okay, so you shouldn't worry too much because coughing, even though it increases, remember the prior probability that somebody had the flu was only 5%. But now if they've coughed, their posterior probability, given that they coughed, went up from 5% to 17. but it's still much below 0.5. So it's still more likely that they don't have the flu even if they coughed. Okay? All right, so simple use of Bayes' rule just to get us all on the same page. Okay, so now why are we doing this? We said before that we're very interested in function approximation, that is coming up with learning algorithms that can learn functions from x to y. Well, if you think probabilistically, if I have an x and I want to predict y, that's another almost equivalent thing I can say is I just want to know the probability distribution over values of y conditioned on values of x. Right? So if I want a spam filter, I could say I'm trying to learn a function from emails to yes or no spam. Or I could say I just want to know the probability that any given email, described by whatever features we're going to use, has spam equals yes or spam equals no. It's kind of the same question. In fact, this maybe is a little bit, here we're really talking about learning probabilities on the possible values of y, whereas at least when we talked about decision tree learning here, we were talking about picking one value for the label after we sort through the decision tree. Here we're asking about, well, what's the probability distribution over possible values? And of course, if it's a Boolean value, like spam or not, you know, if I say, well, the probability that this is spam given the words in the email is 0.9, then obviously the probability that it's not is 0.1. But we'll have other problems where y can take on many values, in which case we might really be interested, like we might be interested in what's the major of a student given the courses that they're taking. And here at CMU, there are many possible majors, and so we might be interested in the full distribution of probabilities over all those possible majors. Okay. So if we want to work with probabilities, then really the single most important thing to understand is joint probability distributions. And here is one. What is a joint probability distribution? It's just an assignment of probabilities to values for a collection of random variables. In this example, I have 3 Boolean random variables, A, B, and C. You can see they can take on each one a 0 or a 1. They're Boolean variables. And for every joint assignment of 0s and 1s to those 3 variables, I've assigned a probability. And here's actually a Venn diagram that describes that. So if you want to make a joint distribution, it's very straightforward. The first step is you make a truth table listing all the combinations of values of your variables. I'm assuming here we have discrete valued variables. Later we'll talk about continuous variables. But for example, if we have m different Boolean variables, then I'll have 2 to the m rows. So here we have 2 to the 3rd rows for the 3 variables. And then for each combination, I simply have to say how probable it is. And since, of course, the values must be something, those probabilities really need to sum up to 1. And so if you add up all the probabilities in this column, you'll see that indeed they sum to 1. Okay? And in terms of our Venn diagram, you can think of this as all the possible worlds, and this being, say, the worlds in which B is true, B is 1, and outside the circle are all the worlds where B equals 0, B is false. And so those 8 numbers really correspond to these 8 regions in that diagram, right? The probability that A will be true and C but not B is 0.1, and if you check it up there, it's the same. Okay, so joint distribution is simply a way of writing down the probabilities for every possible collection of values for the random variables. Now, when we talk about And we could do this. We could go back to the decision tree example that we had where we were predicting whether somebody would play tennis. We could say, well, that's a random variable. And we were basing that on the humidity of the day. We could say that's a random variable. And the windiness, that could be a random variable, and so forth. And we could build a joint probability distribution for those random variables too. And then would be no different than this situation. Okay. So joint distribution. The reason joint distributions are so wonderful is that if you know the joint distribution over a collection of random variables, there is nothing that you can't answer in principle about probabilities or conditional probabilities or joint probabilities over any subset of those variables. So in some sense, knowing the joint distribution over a collection of random variables tells you absolutely everything that there is to know probabilistically about the relationships among those random variables. That's why it's at the heart of what we're doing. So let's look at a couple of those. So for example, I should say that here I've put up a different joint distribution. This is actually an interesting one. My friend Andrew Moore, who went on to become the dean of the School of Computer Science, gave me this data some time ago, but it's data that, real data from a database of people that characterize their gender, male or female, the number of hours they work in the week, more than 40.5 hours or less, and their wealth, binning everybody into either rich or poor, which seems a little bit extreme, but it is. And so we can think, well, there are 3 random variables, 3 Boolean random variables. And just like before, there are 8 possible configurations of values. And here, in fact, are the probabilities associated with each of those joint assignments. Okay. So it's kind of more fun to look at this data than the abstract ABC data. But now we can ask questions about any subset of these variables, joint distributions or conditional distributions. So for example, if we want to know what's the probability that if we pick a random person out of this database, that it will be a poor male, then the way we answer that is we just say, well, there are 8 possible joint assignments. 2 of those involve males who are poor. In one case, there are males who also work less than 40 hours a week, and others it's more than 40, but we don't care about that. And so if we want to know the probability that a random draw will be both, that poor will be true and male will be true, it's just the sum of the 2 probabilities for those 2 rows. Okay, is that clear? Okay, so that's pretty nice. You see what I mean? We can get information out of this joint distribution. Suppose I just want to know the probability of poor being true. Well, there are 4 different rows in this table for which wealth equals poor, and so I'll just sum up those 4 probabilities. What if I want to know a conditional probability? What if I want to know, for example, the probability that you will be male if you're poor? Well, to do that, all we have to do is go back to remember our definition of conditional probability, which is right here. And so what we need to do is we need to, if we want to know male given poor, we should first sum up all the rows that match poor. That's our denominator. And then sum up all the rows that match both male and poor. That's our numerator. And then the ratio, there are the 2 numbers, and there's the ratio. So that's the conditional probability that given poor equals true, that's the conditional probability that male will be true. What's the probability of female given poor? 1 minus that?
0.76 minus this? No.
It is actually 1 minus this, right? Because if we do female given poor, then we'll have female and poor over poor. And so given that you're poor, given that, the conditional probability that you're male given poor plus the conditional probability that you're female given poor equals 1. What's the probability of being a male given that you're rich? Can you do the same thing? No. No. The logic I just explained for why we could get away with summing male plus male given poor and female given poor does equal 1, but male given poor plus male given not poor does not equal 1. Okay? So again, these are things that by the that soon should become rolling off your tongues and they should become second nature. These are intuitions about probability that you should be picking up on as we go. Okay, what if we want to actually train a classifier? For example, we might, just in the same sense that we were interested in predicting the value of the random variable play tennis from the value of several other random variables, here we might, for example, be interested in predicting the value of wealth given the gender and the number of hours worked. That would be a reasonable function to try to learn. And so, in fact, that's very straightforward. It's just another example like the last 3 that we looked at. Once we have the joint distribution, we can get the probability of any given value for wealth given the gender and the hours worked. For example, you should be able to tell me, can we get this? Let's do this one on the fly. This is so simple. So what do we have to do? What are the 2 things we have to get here? We want to get the probability that all of these are true. Wealth equals rich and gender equals female. And hours worked is less than 40. And we want to get the, oops. Wait a minute. Somebody should have corrected me immediately. We want, on the denominator, we just want the G and the H, right? In the numerator, we want all of them. That you're also rich and female and not working too many hours. I should have done one on, instead of wealth, probability of passing a machine learning course. But okay, so what's this? What's our denominator here? How many rows? Just 2, right? Gender is female and few hours. So that would be these 2. So you can see that's like, to the naked eye, 0.277. And what's this numerator? Right, that's just 0.24. So this is like about 0.09 or so. Okay? So you see we could do that for everything, and in fact, in some sense, this table gives us an ability to calculate this conditional distribution, which is analogous to computing this function from gender and hours worked to wealth. And we could do it for any values that we cared about. Okay, so now you see the very close coupling between knowing the joint probability distribution over a set of variables and, well, really knowing anything about the relationship among those. But from our point of view as people who are particularly interested in learning to predict things from other things, then you can see that the joint distribution allows us to do just that. So this is a wonderful thing to know and to have and to learn and to get algorithms to learn. Okay, so in fact, for that example that we just saw, there's really nothing else that's better. If you know the joint distribution over those random variables, then there's no better way to learn the function from x to y, or the conditional distribution from gender and hours worked to wealth. There's no better way than to use that joint distribution. And so if we can do this routinely, then the machine learning course could be cut short. And even though we can use it sometimes, we're actually not done. So does anybody see why?
So the model that we have is quite simple right now. The thing that we are trying to compute is quite simple. And
Right.
it's just, I mean, you have two choices, either 1 or 0, but if you have more. So I think it can get quite complicated for computation.
Right. Good, good. So you actually gave two very good answers, maybe the two of the three main ones. One is, well, we're only talking about simple case here, and simple in the sense that these are Boolean variables. So for example, we haven't talked about what we'll do if they're continuous valued variables, like your salary, which would be a continuous value. And of course, then there'd be too many rows in the table. If we have a real valued variable that can take on infinite number of values, then we can't just build a simple table enumerating those. There are ways around that, but we'll have to deal with them. You also mentioned that there are computational resources involved here that we didn't talk about because we're working on a simple example, and there could be some scaling issues there about the computation. That's also very true. Very true. Does that cover the other answers? I think those are two good ones. Third one I would add, which actually really is a big problem, is it's not always easy to learn the probability distribution. Sounds straightforward. If I have a database with, let's say, 1 million people, and I have those three variables, I could estimate those probabilities pretty reasonably, right? In fact, let's think about that. If I have those three variables, I have 8 rows. And if I had a database with 1 million people in it, then probably there will be many people in each of those 8 rows once I sort them into their row. And I could estimate the probabilities for each row simply by looking at what fraction of the people fall into that row. Right? That would be the common sense thing to do. Okay, what if instead I wanted to get serious, and so I thought maybe wealth was not just a matter of gender and hours worked, but maybe other things like, do you have a college education? Have you taken the machine learning course? What was your grade in the machine learning course? Are your parents wealthy? Are you talking to your parents? Lots of things we could ask as Boolean features to describe people. And so suppose I come up with 100. That's a rather small number. Often in machine learning problems that, say, we're working on in my own group, we often have 1 million variables. So 100 is not like a ridiculous number. But let's suppose we have 100 attributes, 100 variables that describes each person. Then how many rows in that table? Okay, good. 2 to the 100th. Right? If I have m variables, just like before I had 3, so I had 8 rows, 2 to the 3. Now I have 2 to the 100. How big is 2 to the 100? Well, the way I think about it is 2 to the 10th is 1024. So 2 to the 10th is about 1,000. So if you want to turn this into a real number, this is approximately, it's actually greater than, 2 to the 10th to the 10th. or 1,000 to the 10th. Actually, what I should say is it's greater than 1,000 to the 10th. Which is bad, because 1,000 to the 10th is 10 to the 30. Right? If I multiply 1,000 times 1,000 times 1,000, I just count up the number of zeros. I'm going to get 30 zeros after the 1. 10 to the 30 is a bad number. Why? How many people live on Earth? About 1 billion. Okay. Billion is 10 to the 9th? Okay, we have more rows in this table, even with just 100 attributes, than there are people on Earth. So even if our database covers everybody, what fraction of the rows in our table are going to have nobody in them? Most. Right? So even though it sounds straightforward, there is a serious problem here. Which has to do with data sparsity. If we really want to estimate that joint probability distribution accurately, then of course we actually need we need multiple people in each row, so we know what the proportion of the different rows, what the proportion of the probabilities of the different rows really is. And even with only 100 Boolean attributes, we're still in kind of the simple regime here. There's no way we're going to get that. So this is a very serious problem. Even though we would like to know the joint distribution, if we try to estimate it in a simplistic way, then we're going to be restricted to only fairly simple data sets. For example, I don't know what this really is, but I think it's like 2 to the 40 gets us above 10 to the 9th. So we couldn't go up to 50 Boolean attributes and still have enough people on Earth to estimate our probabilities. Okay, so that's key idea number 1 in this lecture. Well, key idea number 1 is joint probability distributions are absolutely awesome. Point number 2 is, unfortunately, it's not obvious how we estimate them once we start scaling up to reasonable numbers of variables. Okay, so what to do about it? The next several weeks in our course are actually about what to do about it, and 2 particular things. One is, well, we want to be smart about how we estimate probabilities. We can't just assume we can do some simple counting thing. And number 2, we want to be smart about how we represent probability distributions, and in particular, we'll be looking into ways in which we can make assumptions about the forms of probability distributions that allow us to have fewer parameters to estimate than the number of rows in the joint probability distribution table. And so these will be the 2 main strategies that we try to use in machine learning so that we can still work with probabilities but have reasonable ways of dealing with the surprisingly sparse amount of training data that's available to us relative to the size of the learning problems that we want to deal with. All right, so now let's take step number 1. That's what the rest of today is about. How can we be smart about estimating probability distributions? Well, let me ask you. Here's the simplest probability estimation problem I can give you. I show you a coin, there it is, got a picture of it. Let's say the coin I will flip, and I'll define a random variable x, which is 1 if it turns up heads and 0 if it turns up tails. Your job is to come up with an algorithm for estimating the probability of it turning up a 1 based on flipping it repeatedly, maybe you would observe that it ends up heads alpha 1 times, and it comes up tails alpha 0 times. So who wants to give me an algorithm which, given that set of experiments, will predict what the probability is that that x will generally be 1? Okay. Don't be shy. Feel free to be simple. Yes?
So we can assume that the probability of head is p and tail is 1 minus p. So through binomial distribution, we can say p raised to power alpha 1 into 1 minus p of raised to power alpha naught. So this is my equation. I need the maximum value of p. So I can take a derivative of this and equate it to 0. So, and I get the value of p from that.
Good. I like that answer. But, and we'll get to that answer. What I'm looking for here is just a heuristic method. Honestly, come on guys, if I say we're in the elevator and I said, I just flipped my coin, it turned up heads alpha 1 times and it turned up tails alpha 2 times, what do you think the probability is? And the door is about to open. What are you going to shout out at me? You're going to say, Tom, it's alpha 1 over alpha 1 plus alpha 0. Don't worry. And then the elevator opens, and we're history. Okay. Now, if you're a mathematician or you had more time, you might actually give a more elaborate answer. But I would agree with you. And I think your intuitions about this are dead on. That's the same thing I would do. Okay. This is a simple way of estimating probabilities. But it's not perfect. Okay. So let's try this algorithm. So you're going to say, this is my estimate of the probability that x equals 1 is this. So that's our algorithm. Okay, so let's try that on 2 cases. First, it turns out in elevator ride number 1, I flipped my coin 100 times. We have 51 heads. So alpha 1 is 51, 49, alpha 0s, alpha 1 over alpha 1 plus alpha 2, or 0, is 51 out of, well, the sum is 100. So that implies the probability that x equals 1 is, I guess, 0.51. Okay? Happy? All right, now in elevator ride B, much shorter elevator ride, we flip the coin 3 times. And this very same algorithm will give us 2 heads, alpha, this case, alpha 1 is 2, alpha 0 is 1, 2 over 2 plus 1, 0.6666. Okay. All right. This second example kind of illustrates what the problem with the simple rule is. Right? If we have a lot of data, then we kind of believe the estimate that we have. Right? Just like if I have enough people in my database to populate, to fill in every row of my joint distribution with a lot of people, then I'm going to believe what I estimate this way. But if I have actually a very small amount of data, then, well, what do you think about this? What do you think the true probability is? I don't know. But if I had to put a confidence interval on this, I'd certainly put a much wider confidence interval, meaning I'm much less sure that this is a good estimate of my coin probability than this one, because this is based on a lot more training data. In fact, it's possible, when I look at this one, I think it's possible that this coin is actually 50% heads. And of course, if you flip it only 3 times, you're going to get not an even number of heads and tails with an odd number of flips. So we have a lot of problems here. Okay, this is actually indicative of what we're facing all the time in machine learning. Remember our example of the database of all people on Earth could only support 40 attributes. We're going to want to be pushing the envelope on building machine learning algorithms that can deal with many variables. In many variables, because in a lot of cases we're trying to learn to predict things and we don't know what to predict them from, and so we want to include a lot of variables as potential predictors. And so we're going to be in a case where we have we're often going to be in a case where we have sparse data to estimate the probabilities. Okay. So let me ask you again your intuition. I liked your first intuition, that we should just look at the proportion of things. But now let me give you the final case. What I really want, this is my real question to you. I want you to give me an algorithm that'll work in the following setting, which some people call online learning because the data is trickling in over time, and you want a hypothesis at any given point in that time series. So you're going to keep flipping, but I want, and initially there'll just be 1 flip, and then there will be 2 and n. I just want a single algorithm that at any given point looks at the counts so far, how many heads, how many tails, what's alpha 1, what's alpha 0, the counts, and gives me a reasonable estimate after each flip. Yes, way back.
Choose a prior and revise the prior each time.
Choose a prior and
Revise it each time using the Bayes rule.
good. Use Bayes' rule. I like that. I think that's great. It's in the same category as this answer, which was use maximum likelihood. I want to ask the same question, but if we're in the elevator and I give you this problem and you don't have time to pull out and write down a lot of equations, what's your gut tell you to do? For one thing, don't forget that I'm showing you a picture of the coin. This is a US government issued minted penny. You probably have some prior idea about what the head's probability could be. It's probably very different from the probability that this pen will land like this, as opposed to like this, right? For a coin, they're usually 50%, unless there's something really weird about that coin. So you do have prior knowledge about that coin. If it's a government coin, probably close to 50%. On the other hand, it's possible that it got run over by a steamroller and ended up bent in some weird way so that it's no longer 0.5. But you should have been a little bit less comfortable with our estimate of 0.66 than our estimate of 0.51 if you took into account that prior information you had. So what does your gut tell you is a good way of a good algorithm that would work here?
See the amount of possibility, like all outcomes,
Mm-hmm.
and just divide 1 by them. By the possible outcomes.
See all the outcomes. Right, so we could still do we could still say alpha 1 is the number of observed heads, x equals 1. And alpha 0 is the number of observed x equals zeros. It's just that I want the same rule to work after I flipped it twice and 3 times and 5 times and 4 million times. I want an equation I can write down here that captures your intuition that the more we flip it, the more I'm going to trust the empirical estimate I get from the data. But before we flip it a lot, I also want to weight some prior information that I have that many government issued coins are 0.5.
0.5 plus this value of alpha 1 on these 2 divided by n.
Like this?
Final
divided by n, the whole thing?
That this whole thing, into 1 by n. As you go longer and longer, the number of flips would go up.
Oh, I see, I see. So here we might like put this as 1 over n, the number total, n is alpha 1 plus alpha 0. It's the total number of flips, right? So we could weight this by 1 over n and, and then we could weight this by n minus 1 over n. Is that what you're kind of getting at? That the bigger n is, the more we want to weight this. I don't know. That doesn't quite work either. Okay, so let me suggest one that I think captures the intuition you're after, which is, what if I say, instead of using this formula, I'm going to use alpha 1 plus, I don't know, I'll say I imagine 20 imaginary hallucinated coin flips, 10 of which are heads. So I'm going to say 10 coin flips that are heads and 10 coin flips that are tails. Okay. So if I do this, suppose I haven't flipped the coin at all. What I'm saying here is, instead of using my observed heads, I'm also going to use some imaginary coin tosses that I just pretended happened, that reflect my prior that the probability is probably 0.5. So I might say, okay, I'm going to imagine that there are 10 heads and 10 tails. And so even though I observe only alpha 1, I'm going to pretend it's alpha 1 plus 10 heads that I observed. And even though I only observe alpha 0 tails, I'm going to pretend it's alpha 0 plus 10 tails. And now when I have 0 coin flips, this ratio is 0.5. That's my estimate. When I have 1 coin flip, then it's either going to be 11 over 21 or 10 over 21. When I have 100 million coin flips, it's not really going to matter that I'm adding in 10. As alpha approaches infinity, my constant 10 that was in there just matters less and less, and in the limit, it doesn't really matter. So in the limit, as alpha, as the number of flips goes to infinity, this converges to this. But when alphas are very small, I haven't flipped the coin very much, then it could be dominated actually by my prior assumption that 50% of the coins are tosses would be 1. Now, why did I say 10 here instead of, say, 100? Well, I could have said 100. In fact, if I did say 100, then it would take even more observed data in the form of alpha 0 and alpha 1 to outweigh my prior assumption. And so the volume of imaginary data that I put in here really kind of captures how sure I am about that prior. If it was a coin that I had just picked up from the US Mint, then I might actually make this 200 and 200 and 200. Because I trust my prior even more strongly, so I'm willing to capture that by contributing even more imagined coin flips according to my prior. Okay, so in general, what I'm going to do, I would just say my general algorithm would be, let's define beta. Beta 1 is the number of hallucinated make some room. Hallucinated x equals 1s. And beta 0 is the number of hallucinated x equals 0s. And now I'm just going to replace my formula in general to alpha 1 plus beta 1. There. So now I'll just, instead of taking our old simple strategy was to take the fraction of observed coin tosses that came out heads. Here we're going to take the fraction of observed plus imagined coin tosses that turn out heads. And beta, well, you can pick beta. The more confident you are in your prior, the more imagined, hallucinated coin tosses you can enter into this expression. Okay. So I like this formula for two reasons. One is it has this very nice property that if I pick my betas before I start flipping, and I flip infinitely long, eventually it doesn't really matter what those betas were. They're dominated by the alphas, which are much bigger. And so it has a nice property that I can use my priors when I have sparse data, low values for my alphas, not very many flips. But those priors asymptotically don't really matter if I have enough data. That's one reason I like it. Second reason I like it is there's actually a really nice mathematical justification for this in terms of Bayes' rule, which you're about to see. Okay, but this is key idea. Well, we had joint probability distributions are awesome. That was key idea one. Sadly, we can't estimate them in complicated cases in straightforward ways. So we have to do something smart. And key idea number 3 is, here's something kind of smart because it lets us bring in prior assumptions in a way that's fail-soft. The more data we actually observe, the less and less it matters what those prior assumptions were. And this happens to be correspond to one of the two main ways of estimating parameters, in fact. Question, yes?
What if you're looking at you're going into more complicated situation and you have no reasonable way to have a prior?
If you have no reasonable way to have a prior, you're toast. Really, if you can only flip, you can only test a random variable twice, and you have no prior, you're going to have a pretty unreliable estimate of what that probability is. I can't think of any other way out. Now, the prior can have a lot of different forms, and depending on the probability distribution in question, you may have all kinds of different ways of having different types of prior assumptions about that. Like, for example, we'll be seeing ways where instead of saying, here's what I think the values are, we say things like, well, I think these two random variables are independent, likely to be independent. And I'm now trying to just estimate the probability distribution on their joint values. So we'll see all kinds of different shapes of priors. But really, if you have none and very little data, that's the place you don't want to be. Does anybody see a way out? No free lunch. Okay, so what we just saw, your two methods that you gave me in the two elevator rides, one was, well, just look at the fraction of coin flips that turn up, observed coin flips that turn up heads. That actually turns out to be what statisticians, after several pages of mathematics, announce is the correct way to do it. It's called the maximum likelihood estimate. And that's one of the two dominant principles for estimating probability parameters. Actually, let me back up. The coin flip example is a very simple example where there was just one number, one parameter we're trying to estimate. What's the probability that this coin in particular will end up heads? You gave me very good advice on how to do that. more generally in this course, we're going to sometimes be estimating many parameters at once. For example, if we want to estimate a joint distribution, there are going to be a lot of rows in that table and a lot of different probabilities to estimate. And so in general, I'll think of theta as a variable that we'll use to represent the set of parameters being estimated. In this case, the coin flip example is just one number. And one of the ways, if you ask, what's the principle by which we would like to estimate theta? One principle is to choose the parameters that maximize the probability of the data we did observe given those parameters. And if you work out the math on that, you find in our coin flip case, it's exactly this. A second principle is to say, well, if we have some prior knowledge, then we can actually instead pick the parameter that maximizes the probability of theta given the data and our priors. And if we do that in the case of the coin flip, we get exactly this. We get exactly this formula. Okay, so, and when I say we're going to maximize the probability of theta given the data, remember that's, according to Bayes' rule, the probability of the data given theta times the prior on theta divided by the probability of the data. And so if we're trying to estimate the theta that's most probable given the data, then it turns out we want to, one way to do it is to use Bayes' rule, express it this way. By the way, you notice right away that the bottom here doesn't even involve theta. So if we want to maximize this, all we really need to do is maximize the numerator. And the numerator is just the maximum likelihood quantity that we were estimating, that we were trying to maximize, but now multiplied by a prior. Okay, so any comments, questions on these principles? The whole point, the reason I wanted to come at it this way is when I first had to learn this stuff, it took me a long time to sort through a lot of equations to figure out in the end that it was a very, very simple principle. And so I wanted to start by just asking your gut reaction of how you would estimate these things, because I think they're very reasonable, heuristically, strategies for doing these estimates. It does turn out that we can derive them according to these two principles, and that's what I want to do next. So any comments or questions on this before we look at the formal version of this? Which one's better? If you have very good priors, then I will usually go with this one. Because as we said, as the volume of observed data grows, as the counts for the number of observed heads and observed tails grows, then the hallucinated data will just kind of not matter in the limit. And so if you do have very good priors, I will usually go with this. You can think of this as just this is equal to this when you have infinite data. The two reasons we sometimes go with this instead of this is we don't have good priors, so we don't know what to put there. The second reason is complexity of the computations. Okay, all right, so now let's look at maximum likelihood estimation. So this is method number one. The question at hand is, we have some observed data, in our case, still our coin flip. And we want to pick, we've decided that as a matter of principle, the way we're going to choose learn the value of our probability parameter is to choose the value that makes the data that we've observed the most probable over all possible values. So we might choose theta equals 0.9, 0.8, 0.7, 0.6, 0.5, 0.4. One of those values will make this observed data that we have most probable, and that's the value we're going to choose. Okay, so let's look at that. Suppose we flip a coin, let's say 5 times. And so I get a sequence of flips like, turns out heads, then it turns out tails, tails again, heads again, heads again. Okay, those are 5 flips. Now, if I say I'm defining theta to be the probability that x equals 1, we don't know what theta is yet. We're about to estimate it. But I'll just tell you, let's use the symbol theta to represent that probability. Then what's the probability of me flipping independently 5 different times the same coin so that I get a set of flips which are independent and identically distributed, meaning they come from the same probability distribution. It's the same coin, and they are independent flips. What's the probability that I'll see that sequence of 5?
0.6.
Pardon me?
0.6.
0.6? It depends on what theta is, right? You have to give it to me in terms of theta. So like, what's the probability that the first flip will be a 1? Theta. This p of x equals 1. It's theta, right? So the probability of this first one is theta. That's what we set up here. We're going to use. Okay. What's the probability that I'll get a 0? 1 minus theta. This one, again. Oh, so you see what's going on here. Every time I get a 1, the probability is theta. Every time I get a 0, the probability is 1 minus theta. What's the probability that all 5 of those things will happen if they're independent flips? Right. Then it's just the product of these. Right? So now the probability of the data, which is this set of 5, given theta, is the product of these things, which is simply theta cubed times 1 minus theta squared. Right? In fact, in general, if I observe alpha 1 heads and alpha 0 tails, what's the probability? Right. 3 here was just alpha 1 in our case. 2 here was just alpha 0 in our case. Okay. So the probability of the data, depending on what theta is this expression, where the data can actually be summarized simply by these counts of the observed number of heads and tails. We don't really care about the sequence because these were independent, identically distributed flips. And, you could have cheated and read this. Okay, so there it is. That's the probability. But you see, it's very easy. You could have figured that out if I hadn't written it down. So now, think back to freshman calculus. If you want to know what's the value of theta that's going to make this probability as big as possible, this probability maximized, what do? Right, right. This is one of those functions where we can take the derivative and set it to 0. So let's do that. We're interested in I'll put a little hat to indicate that this is our estimate of theta. We don't know what the true theta is. But our estimate of theta is going to be the value that maximizes, I wrote the log of the data, of the probability of the data given the theta. That's because it's going to turn out the arithmetic is easier to work, the calculus is easier to work if we maximize the log of it rather than it. And if you have a function that you're trying to maximize, you get the same answer if you maximize that function or if you maximize its log. Log is monotonic in the function. And in our case, we figured out just on the previous slide what the probability of the data given theta is. That's called the data likelihood in many corners. And now we're just going to set that derivative to 0. Okay? So that's actually pretty straightforward too. I'll take you through the first few steps, and on your homework you're going to get a chance to look at these estimates in more detail. But so what we want to do here is we want to set the derivative of this thing to 0. And so let's take the derivative with respect to theta of this thing is just the derivative. Well, since we're taking the log of this, I can write it as alpha 1 times the log of theta plus, remember the log of a product is the sum of the logs. So I can write this as alpha 1 times log theta, plus alpha 0 times log of 1 minus theta. Okay? And now I can just, since this is a sum, I can just take the derivative of each one. So here we have alpha 1 times derivative of log theta with respect to theta. But see, I put this little nice hint in the corner here. In case you forgot, as I had, and I had to look it up, the derivative of the log of theta with respect to theta is just 1 over theta. So I'm just going to use that fact. Plus theta times the derivative of this thing. But here I can use the chain rule, right? So this quantity is just the derivative of log of 1 minus theta with respect to 1 minus theta times the derivative of 1 minus theta with respect to theta. Chain rule. And so now it becomes easy because this derivative is just minus 1, right? And this derivative is 1 over 1 minus theta by this same rule up here. If I substitute up here theta minus 1 for theta, then I get that. Okay, so now there's my answer. 0 equals alpha 1 times 1 over theta minus 1 over 1 minus theta. So if I just solve for the theta, whoops, wait a minute, there's an alpha 0 in here I left out. Okay, so that's the answer. If I just pick a theta that zeros this, then we're there. And you can work this out at home, but it's easy to verify that this implies that theta equals alpha 1 over alpha 1 plus alpha 0. Isn't that beautiful? So your first intuition that said we should just look at the fraction of these things that come up heads was actually consistent with the principle, the underlying principle, that we should pick the value of theta, we should estimate the probability of heads by picking the value of theta that maximizes that quantity at the beginning, the probability of the observed data given theta. Let's pick the theta that makes the probability of the data as big as possible. That makes the data likelihood as great as it can be. Okay, so here's the summary, the big picture. If we have a maximum likelihood estimate of a single Boolean valued variable, like our coin, but in general, if we assume what's called a Bernoulli distribution on that random Boolean variable, Bernoulli simply means that we represent the probability distribution by theta, a number. Then here we're assuming each flip yields a Boolean value which is independent. In fact, even though I could write it as if x equals 1, then the probability is theta. If x equals 0, it's 1 minus theta. This mathematical expression is another way of writing that same if statement. Right? If you plug in x equals 1 here, you get theta, and this term is out. If you plug in, or it doesn't zero out, it becomes 1, so it's 1 times theta. If you plug in x equals 0, then the first term becomes 1, and the second term is just 1 minus theta. So this is a tricky, a nice mathematical way of representing if statements. And it turns out to be useful form because it makes it easy to derive these kind of expressions that we did for the full data likelihood. But then when we maximize this, we pick the theta that maximizes it, we get exactly that. Okay, so let's look at our second principle. This idea of hallucinating examples and adding them in. Well, principle number 2 says that we could choose parameters that maximize the probability of theta given the data, assuming that we do have some prior that we want to put on theta. And then we can use Bayes' rule and solve for the theta that maximizes this quantity. So let's take a look at that. In this case, I want to propose a prior distribution shown here. I want to say, what if I happen to use this prior? It's called a beta distribution. It's a bad box. I want to use that distribution as my prior. Then to maximize the probability of theta given the data, I want to maximize the numerator of Bayes' rule, that is the probability of the data given theta times the prior. We already saw before in our maximum likelihood estimate, the first method, we already agreed that the probability of a collection of coin flips would be just theta to the alpha heads times 1 minus theta to the number of tails. And if we use this prior that I'm suggesting, you'll notice that this prior has the nice property that it looks very similar in form to this data likelihood that we calculated. By the way, the denominator here is just a term that makes sure the probabilities integrate out to 1. Here theta is a continuous value, so just as before in the joint distribution, we had to make sure the probability summed to 1. Here, the integral of the probability densities needs to integrate to 1. And that's all beta is doing. It's just making sure this is a well-formed probability distribution. So, but the real action is in that numerator. So now if I actually calculate this quantity, what do I get? It's beautiful. I get, well, this quantity times this quantity. So my numerator is actually theta, and here I have an alpha heads. Those are the observed quantities. But there's also this term here. So it's, oops, beta heads minus 1. And then there's another term, which is 1 minus theta to the alpha tails plus beta tails minus 1. Over, and then I'll have another normalization constant that makes sure it sums to 1. But you see what happens, the reason that I actually chose that form of prior is that when I then get the posterior probability, the probability of theta given the data, it ends up multiplying that expression with that one, gives me something of this form. And guess what? You guys already know what the optimal how to maximize this with respect to theta, that's what we just did. Only when we just did it on the previous case, we were using, in this exponent, we just had an alpha h. And now we have this other expression. And here we just had an alpha tails. And now we have this other expression. But the arithmetic is exactly the same. The derivation is exactly the same. It's just that we're substituting this more complicated thing, which includes these betas, which do in fact correspond to imaginary examples. And so this suggests, in the end, this leads to the maximum a posterior probability estimate of theta is just like before. It's alpha heads plus beta heads. There's a -1 in here in this case, which comes from this, just the way that the beta distribution is defined, over alpha heads plus beta heads -1 plus alpha tails plus beta tails -1. So you can go ahead and do the derivation again, but it's really the same calculus that we went through before. It's just that this will be the exponent instead of just the alphas. And so you can see the role of the betas, since this is what our estimate is going to be. The role of these betas in that beta distribution is really to play the same role we talked about intuitively. It's to be imaginary hallucinated examples. And the more sure we are, the bigger we make those betas, the less sure we are about the priors, the smaller we make them. But it's exactly the same intuition we talked about. And so to look at the big picture, here's the big picture, or the summary picture. We have our coin flip. We say the likelihood, that is the probability of the data given we observe alpha heads and alpha tails as counts when we flip. If we use this prior, called a beta distribution, then the posterior is actually in the same form as this, except that instead of having beta as its arguments, it now has beta plus alphas. And when we get the map estimate, which maximizes this over all possible values of theta, we end up, the value that maximizes it is exactly this. Okay, so this generalizes, by the way, and I put some additional slides in to show you, for example, if it's not a coin but a dice that you can roll that has multiple sides, very similar kind of strategy. It turns out very much the same. And so to summarize, here are the key ideas. 1, joint distributions are awesome. B, estimating the probabilities for these things, somewhat of an issue. And since we're always trying to push the envelope by having lots of variables and we want to learn as well as possible from limited data, we need smart ways to estimate probabilities. You just saw today the 2 main ways. They're based on 2 principles: maximum likelihood, which means just pick the value of the parameters that makes the observed data most probable, or method 2, which was to invoke a prior, is to maximize, it's called MAP estimates, for maximum a posteriori probability estimate, MAP estimate. That's to maximize the probability of theta given the data instead of the probability of the data given theta. Some of the terminologies here: probability of the data given theta is often called the likelihood, the prior and the posterior. You notice that trick that I did with the beta, using the beta distribution, choosing that particular form of prior that made the arithmetic nice. That's called a conjugate prior. In general, a prior is the conjugate prior for some likelihood function p of data given theta if the functional form of those two are the same. In our case, they were the same. They were these theta to the exponent times 1 minus theta to an exponent. And that was true both for the prior that we made up and for the form of the data likelihood. So you'll often hear, if you read papers on this, you'll also often see people talk about, oh, we found the conjugate prior for this likelihood function. They're celebrating that because it means that their arithmetic becomes easy, and in many cases, it actually means that there are parameters in that prior that can be thought of as hallucinated examples as a way of capturing your prior knowledge about what you think the parameter might be. Okay, so that's a bunch of stuff. You'll get a chance on the homework that's out today to look at this in a little bit more detail. Come to recitation tomorrow if you have any questions on it, and we'll catch you later.